Integrated thermal protection system, triple-layer active cooling for Starship. Eliminate tiles. Enable rapid reuse. Reach Mars. With a provisional patent filing in October 2025, we're targeting the nose cone and belly sections with 44% mass reduction and 90% faster turnaround. Ceramic tiles are the bottleneck to rapid reusability. The current system faces tile gap vulnerabilities leading to localized overheating, attachment failures requiring extensive post-flight inspection, and refurbishment times of 2 to 4 weeks between flights. Reliability concerns persist, especially in the nose cone and belly high heat zones, with a mass penalty from tiles plus separate load-bearing structure. Starship's goal is aircraft-like operational tempo, but tiles require weeks of refurbishment after every flight. SpaceX needs to eliminate tile gaps, reduce turnaround time to days not weeks, increase reliability, reduce mass, and enable Mars missions with long-duration protection. Here's how the 3 layers work together. Layer 1, the microchannel fluid cooling, uses embedded channels with liquid sodium or supercritical CO2 to handle 5 to 10 megawatts. Layer 2, the gas cooling substrate, is a porous ceramic that provides transpiration cooling with 3 to 5 megawatts capacity. Layer 3, the RAM air cooling system, is self-powered by re-entry pressure flowing through the carbon fiber honeycomb structure to deliver 10 to 15 megawatts. Together, these 3 layers provide 18 to 30 megawatts of cooling capacity per 10 square meter section, far exceeding what ceramic tiles can achieve. The integrated TPS is 10 times better than ceramic tiles. For the nose cone, mass reduces from 320 kilograms to 180 kilograms, a 44% reduction. Refurbishment time drops from 2 to 4 weeks to 1 to 3 days, a 90% reduction. Heat removal increases from passive only to 18 to 25 megawatts active, a 10x increase. Structural strength increases 2 to 3 times with integrated design. Reusability extends from 10 to 20 flights to over 100 flights, a 5 to 10x increase. And tile gap issues are completely eliminated, a 100% reduction. Additional benefits include self-healing capability with autonomous crack repair during re-entry, micrometeorite protection with Whipple shield for Mars transit missions, TEG backup power using thermoelectric generators powered by re-entry heat, and Mars compatibility using the Martian atmosphere for cooling. Phase 1 targets the nose cone, the highest heat and most critical failure point. The nose cone has a surface area of approximately 10 square meters, peak heat flux of 100 to 200 watts per square centimeter, total heat load of 10 to 20 megawatts, and duration of 5 to 10 minutes during re-entry. The ITPS configuration includes a 2 to 3 mm CMC outer skin with embedded microchannels, 5 to 10 mm porous silicon carbide foam for gas cooling, 30 to 50 mm carbon fiber honeycomb core with 15 to 20 mm hexagonal cells, for a total thickness of 40 to 65 millimeters and total mass of 180 kilograms, compared to 320 kilograms for tiles plus structure. Cooling capacity includes 5 to 10 megawatts from microchannel fluid, 3 to 5 megawatts from gas substrate, and 10 to 15 megawatts from RAM air, totaling 18 to 30 megawatts, providing a 1.5 to 3 times safety margin above peak load. Manufacturing uses co-cured assembly in an autoclave with a single bond cycle for strongest integration and modular replacement if damaged. The system features autonomous repair during re-entry through 3 self-healing mechanisms. First, the outer CMC skin uses high-temperature oxide healing. The material is silicon carbide CMC with 5 to 10% boron carbide. At temperatures of 1200 to 1500 degrees Celsius, boron oxidizes to borate glass which flows into cracks and solidifies. Healing time is 5 to 10 minutes during re-entry with 80 to 100% strength recovery. This has heritage from jet engine turbine blades at GE and Rolls-Royce. Second, the microchannel system uses microcapsule-based healing with DCPD or epoxy in 10 to 100 micrometer microcapsules. Pressure drop ruptures capsules, monomer flows, polymerizes, and seals the crack in 1 to 10 minutes with 75 to 90% strength recovery. This has heritage from self-healing concrete and aerospace composites. Third, the honeycomb core uses a vascular network with hollow carbon fiber channels filled with 2-part epoxy. Damage ruptures channels, components mix, cure, and restore strength in 10 to 60 minutes with 60 to 80% strength recovery. Multiple healing cycles are possible. The result: the system can repair microcracks autonomously during and after re-entry, extending lifespan to over 100 flights. For Mars missions, we integrate Whipple shield protection against micrometeorites. The challenge: 6 to 9 month transit exposes the vehicle to micrometeorites traveling at 10 kilometers per second. A single impact can compromise standard thermal protection. Our integrated Whipple shield design uses the outer CMC skin as the bumper to fragment incoming particles. The honeycomb core absorbs debris energy. The pressure hull remains intact. Performance metrics: protects against 1 to 5 millimeter particles at 10 kilometers per second with minimal mass penalty of 15 to 20 kilograms per 10 square meters. This is mission critical for long-duration missions without ground refurbishment and protection during aerobraking in the Martian atmosphere. The ITPS enables Mars duration survivability that tiles cannot provide. The system includes self-powered cooling using re-entry heat. The challenge is that active cooling requires pumps, and pump failure equals system failure, so we need backup power for redundancy. Our thermoelectric generator solution places TEGs between the hot outer skin at 1200 to 1500 degrees Celsius and the cool honeycomb core at 200 to 400 degrees Celsius, creating an 800 to 1100 degrees Celsius temperature gradient. Using scutterudite or half-Usler alloys for high-temperature TEGs, we achieve 500 to 1000 watts per square meter power output during peak heating. System integration has TEG's power backup electric pumps for fluid cooling, charge batteries during the 5 to 10 minute re-entry, and provide power for post-landing inspection and maintenance. Redundancy includes primary pumps plus TEG-powered backup pumps. Benefits include zero external power required during re-entry, autonomous operation, reduced single-point failure risk, with heritage from Mars rovers using RTGs and deep space probes. The implementation follows 3 phases. Phase 1 targets the nose cone over months 1 to 18. Months 1 to 6 cover design, analysis, material selection, and manufacturing trials. Months 7 to 12 involve building a prototype nose cone and ground testing for thermal, structural, and vibration performance. Months 13 to 18 include flight testing on a Starship test vehicle to validate performance. The deliverable is a flight-qualified nose cone ITPS at a cost of $15 to $25 million. Phase 2 targets the belly section over months 19 to 36, scaling the design to approximately 150 square meters, developing manufacturing processes, building prototype belly panels, conducting ground testing, and flight testing the integrated nose plus belly ITPS. The deliverable is a flight-qualified belly ITPS at a cost of $25 to $40 million. Phase 3 covers full vehicle coverage over months 37 to 60, expanding to flaps, aft section, and other high heat zones, with full vehicle integration and Mars mission qualification. The deliverable is a Mars-ready Starship with full ITPS coverage at a cost of $40 to $60 million. Total development cost is $80 to $125 million over 5 years. The licensing value is $60 to $100 million, covering phases 1 and 2, with SpaceX funding phase 3 internally. We propose a strategic partnership framework for technology transfer and operational integration. The engagement model includes 3 components. First, technology licensing, full access to patent portfolio, technical documentation, and manufacturing IP for Starship integration. Second, milestone-based integration, phased implementation aligned with Starship development cycles from prototype to flight test to fleet deployment. Third, technical advisory, dedicated engineering support for TPS integration, testing validation, and Mars mission planning. The goal is seamless capability transfer, enabling SpaceX to own the manufacturing and operation of the ITPS for the long term. The strategic value includes operational value through aircraft-like tempo, eliminating refurbishment bottlenecks to enable rapid reuse and high flight cadence. Performance value through increased payload to orbit, as significant mass reduction in nose cone and belly sections translates directly to payload capacity. And strategic value through Mars mission enablement, where self-healing and micrometeorite protection are critical enablers for long-duration deep space missions. No one else has active TPS for reusable vehicles. SpaceX Starship currently uses ceramic tiles which are passive with tile gap issues and long refurbishment, and our solution is integrated TPS. Blue Origin New Glenn uses ablative TPS which is single-use and not reusable, giving us the advantage of 100+ flight reusability. NASA Orion uses an ablative heat shield that's single-use and not designed for reusability, giving us the advantage of active cooling and reusability. Space Shuttle used ceramic tiles that were passive and required months of refurbishment, giving us the advantage of 90% faster turnaround. X-37B uses advanced tiles that are passive, classified, with limited reusability, giving us the advantage of active cooling and transparency. In the patent landscape, SpaceX has 0 patents on active TPS for Starship, Blue Origin has 0 patents on active TPS, NASA has historical patents on shuttle tiles that have expired, and our patent covers the novel combination of triple-layer active cooling plus carbon fiber honeycomb plus self-healing plus TEG. Conclusion: we have a 5 to 10-year technology lead with no competing patents and first-to-file advantage. We address technical and programmatic risks comprehensively. Technical risk 1 is microchannel clogging or failure, mitigated by redundant cooling layers with gas plus ram air, self-healing seals, and filtration systems, resulting in low residual risk due to 2 backup cooling layers. Risk 2 is honeycomb delamination under thermal cycling, mitigated by co-cured assembly for strongest bonds, high-temp adhesives, and thermal expansion matching, resulting in low residual risk due to extensive heritage in aerospace composites. Risk 3 is self-healing insufficient for large damage, mitigated by self-healing targeting microcracks only with modular panel replacement for major damage, resulting in medium residual risk acceptable for prototype phase. Risk 4 is TEG power output insufficient, mitigated by TEGs being backup only with primary pumps powered by vehicle systems, resulting in low residual risk as TEGs provide redundancy, not primary power. Risk 5 is manufacturing complexity and cost, mitigated by phased approach starting with nose cone first and leveraging SpaceX's composite manufacturing expertise, resulting in medium residual risk acceptable for high-value innovation. Programmatic risk 1 is development timeline exceeding 18 months for phase 1, mitigated by experienced team, clear milestones, and parallel testing activities, resulting in low residual risk with conservative timeline and margin. Risk 2 is flight test revealing unforeseen issues, mitigated by extensive ground testing first, instrumented flight test, and backup tile system for first flight, resulting in medium residual risk acceptable for test program. Risk 3 is SpaceX priorities shifting away from ITPS, mitigated by licensing agreement including minimum development funding commitment, resulting in low residual risk with contractual protection. Overall risk assessment: medium risk, high reward, acceptable for breakthrough innovation. Our innovation team is focused on solving the fundamental challenges of rapid reusability. The concept architecture team specializes in advanced TPS design and first principles engineering, focused on solving the fundamental physics of rapid reusability through novel material integration and active cooling architectures. The technical research team focuses on material science and thermodynamic modeling, developing the theoretical frameworks and simulation models for self-healing mechanisms and multi-layer heat rejection. On intellectual property, we have filed a non-provisional patent application on December 17, 2025. The status is filed with strong priority established. The scope covers integrated active cooling and structural TPS. Key claims covered include integrated CMC honeycomb structure, triple-layer active cooling architecture, and autonomous self-healing mechanism integration. Our implementation strategy is clear. SpaceX builds the capability internally. We provide the IP license and technical guidance to enable rapid vertical integration. Strategic alignment with Mars mission architecture is critical. The ITPS development timeline synchronizes with Starship's evolution. From 2025 to 2026, we focus on development and testing with ITPS prototyping and ground validation. From 2027 to 2028, flight integration with nose cone retrofit and orbital tests. In 2029, fleet deployment with full-stack integration for the Mars fleet. And 2030 and beyond, operational capability for crewed missions aligned with the Mars transfer window. 3 key alignment points drive this timeline. First, vehicle evolution. ITPS development aligns with Starship's transition from prototype testing to operational fleet deployment. Second, reuse requirements. As flight cadence increases, the need for zero refurbishment TPS becomes the critical path for operational efficiency. Third, mission readiness. Targeting TRL-9 readiness specifically for the 2030 Mars transfer window to support long-duration crewed flight. The ITPS is designed to be ready when Starship is ready for Mars. Thermal protection for the next 100 years. Elon's Mars vision calls for humans on Mars by 2030 and a self-sustaining city by 2050, making humanity a multi-planetary species. ITPS's role includes rapid reusability, enabling 10+ flights per vehicle per year for aircraft-like operations, mass efficiency at 44% lighter than tiles with more payload to Mars, long-duration reliability with self-healing for 100+ flights and Mars transit protection, and Mars-native capability using Martian atmosphere for cooling during entry, descent, and landing. Starship plus ITPS equals Mars transportation system. On Earth, we reduce launch costs to $10 to $20 per kilogram versus $1,000 to $2,000 per kilogram today, enable megaconstellations, space stations, and lunar bases, and dominate the commercial launch market. On Mars, we enable cargo and crew missions with rapid turnaround, support in-situ propellant production and return flights, and build a self-sustaining Mars colony. This is bigger than a licensing deal. This is infrastructure for humanity's future as a multi-planetary species. The appendix provides detailed technical visualizations of the multi-layer architecture. The thermodynamic flow path illustrates the three-stage cooling hierarchy with microchannel fluid cooling, gas cooling substrate, and RAM air cooling working in concert to manage heat flux. The physical material stack demonstrates the integration of the outer CMC skin with the porous substrate and RAM air honeycomb core, showcasing the load-bearing capability of the complete assembly.